this video, we'll explain the rule of quantifier exchange. So the way the rule of quantifier exchange works is, suppose we have the formula, it's false that for all x, ax. Well, by the rule of quantifier exchange, that becomes there exists an x such that it's false that ax. If you think about this, it makes sense. If it's false that everything has the quality ax, well, then it follows from that there must be something that doesn't have that quality. Likewise, if we have the formula, it's false that there exists an x, ax. Well, then that becomes the formula for all x, not ax. And again, this makes sense. If it's false that there exists a thing such that it has the quality a, well, then that must mean that everything doesn't have the quality a. So we will use this. You'll notice also that this rule is a two-way rule because it has the 4 dots in between it. So we can go either direction. So if we had the formula, there exists an x such that it's not an ax. From that we could derive it's false that for every x, ax. However, we're mostly going to go in the direction of pushing the negations in. Because if we have a formula that has negations on the outside of it, so we have a negated universal or a negated existential, we can't do anything with that. We can't use our rule of universal quantifier out on it or existential quantifier out because the universal quantifier or the existential quantifier are not the major operator. The negation is. So we need to move that negation in so that we have a quantifier on the outside, and then we can use a quantifier rule on it. So we're going to use this rule of QE in order to derive universal statements. And we'll do so using reductio. So every time that we want to derive a universal statement, instead of having a rule of universal quantifier in, what we will do is we will assume the opposite, so assume that that universal statement is false, and then we'll use the rule of QE to push that negation in, and then we can work with it. And then we will get a contradiction, and then we can prove what we were setting out to prove, which is the universal statement. So I'll show how this works in a proof. Okay. So suppose we have two premises. There exists an x. For all x, there exists an for all x, if ex, then ix. And then for all x, if sx, then ex. And our conclusion is then, for all x, if sx, then ix. So since we're trying to derive a universal formula, we need to assume its opposite, and then try to get this by reductio. So we're going to assume for all x, if sx, then it's false that for all x, if sx, then ix. So that means we need an ADC column. And now we need to use the rule of quantifier exchange on this before we can do anything. And I would always suggest doing any quantifier exchange steps before you do any instantiations. Because if you did an instantiation on lines 1 and 2, well, you're going to see how that's going to lead us into problems. So let's do the quantifier exchange step first. So all that happens is that you switch the quantifier. So if you start out with a universal, you're going to end up with an existential. And then you move the negation in just past the quantifier. And nothing else changes. And that's by 3QE. And so that will depend on 3. So now that we have line 4, you can see why it would have been a mistake to instantiate lines 1 or lines 2 first, because then we wouldn't be able to use the same letter when we instantiated line 4, because it's really an existential. So that's why we always want to do our QE steps first so we can see what we're really dealing with. Okay, so we're going to instantiate line 4. So we'll get not, it's false that SA arrow IA. And that's by 4 existential out. And that'll depend on 3. And then I'm going to use the rule of arrow to get rid of that negation on the outside. So that'll give me SA and not IA. And that's by 5 arrow. So that'll depend on 3. Okay, and then we instantiate the formulas on line 1 and line 2. So that's 1 universal out. It'll depend on 1. And then SA arrow EA. So that's by 2 universal out. It'll depend on 2. Then we get SA from line 6 ampersand out. So that's 3. Depends on 3. And then we can get EA by 8, 9 arrow out. So that'll depend on 2 and 3. And then we can get IA by 7, 10 arrow out. So that'll depend on 1, 2, and 3. And then we can get not IA by 6 ampersand out, which that will depend on 3. Now you can see I've run out of room. But you can see how this proof is going to finish up. I now have what I need for the contradiction. I have IA and not IA, so I'll put those two together, and then I'll be able to derive my conclusion by dash out. From lines, it'll be lines 3 through 13 dash out will give me my conclusion. So that's how we do the rule of QE, and that's how we derive a universal formula in our system.